We're going to continue discussing classification methods. So we just spent some time first on naive Bayes, which is sort of, you can think of not as a specific classification method, but rather almost kind of a principle for making a classification method. That is, we assume that our parameters are independent, and then to get our specific classifier, we just need to specify a univariate distribution for each of our features. That was our naive Bayes model. Then we looked at another classification method, which is our Gaussian discriminant analysis, where we did something very similar to the naive Bayes model, but instead used a multivariate normal distribution for our parameters. We're going to continue talking about classification. We're going to look at another model, logistic regression, and let's define it and show how we learn a logistic regression model, and then let's look at the comparison between the methods that we've just looked at. Okay, so a logistic regression model makes the following assumption. Here is the distribution of y given x. It's a Bernoulli distribution for y with a particular probability parameter, which is the following. You take our feature vector, multiply it by w and add b. W and b are going to be the things we learn when we learn logistic regression model. Put it through the logistic function. The logistic function is the following. Sigma a, by the way, unrelated to the use of sigma for variance. This is the, sigma is used here because it's an S-shaped function. Sigma of a, 1 over 1 plus exp of minus a, by the way, equivalently written as exp of a over exp of a plus 1. We've seen the logistic function and, in fact, logistic regression in general before, so we'll go over this pretty quickly. Note that we're defining this model very differently than we did those generative models in the last chapter. Those generative models were defined like this. We imagined that x is a function of y, and we defined some generative model of x given y and just use a categorical distribution for y. The logistic regression model we're defining kind of in the opposite way. We're assuming here that y is a function of x, and that y is determined according to kind of this complicated distribution here. That is, that y is distributed according to that Bernoulli distribution with this probability parameter here. So what we were looking at in the last section, the naive Bayes model and the Gaussian discriminant analysis, those are called generative classification models. In this section, we're going to look at logistic regression, which is an example of a discriminative classification model. So generative in the case, generative because we're specifying a full distribution, probability of x comma y. Logistic regression is discriminative because we're specifying just probability of y given x. Notice that nowhere here have we defined the probability of x by itself, which we would need to do to make this a full probabilistic model. Also note that once we've learned this model, we don't have to apply Bayes' rule in the way we did with the, for example, Gaussian discriminant analysis model. Once we've learned this model, well, to get what we want, which is the probability of y given x, we just plug in the features for our particular example into this expression, and we get out the probability that we're looking for. So let's see how we learn a logistic regression model. So if we write out the negative log likelihood of our model, what we're looking for is the probability of data given observed values x, and our parameters w. In the model we specified on the last slide, we had two sets of parameters, w and b. Just for notational simplicity, let's use just w. This is without loss of generality because we could just add an additional feature to our x's that's one for all the examples. And it's not too hard to show that such a modification gives us exactly the same model as if we added our b parameter. So we're going to assume there's no b parameter, b for bias, by the way. And if we take the log of that, we get the negative log likelihood. And we can write it as follows. By the way, notice that because our data has just y, that is, we have no generative distribution for x, we nowhere in our negative log likelihood is going to be terms associated with the probability of x, because we don't have any generative distribution for x. It's going to be just that Bernoulli distribution. So here's a way to write it. We've just split it out into two terms, one with y and one with 1 minus y. This is just another example of that indicator function trick, because note that if y is 0, then this term goes away and we have just this term, and if y is 1, the second term goes away and we have just the first term. And we have a sum over our different examples. So our ultimate likelihood is just going to be a sum of one of these mu values for each of our likelihoods. And we're defining mu of n to be logistic function of w x n. Again, ignoring the b for bias term here. Let's take the derivative of this negative log likelihood. It's going to turn out that we don't have an analytical solution, so we're going to use a gradient-based solution. But in either case, whether we want the analytical solution or the gradient-based solution, we're going to need to take the derivative. So let's do that. So here's the derivative of the negative log likelihood. We're writing this as the full derivative with respect to all the w's, not just the partial derivative. You can do this using the partial derivative as well. So here we've written this out. Notice that I've just pushed the derivative in through the sum, and note that the yn is constant for our data. It's constant in w, so we end up with, we need to find the derivative of each of these terms respectively. The derivative of log mu of n and the derivative of log 1 minus mu of n. So to do that, we're going to use the chain rule. So in order to figure out how to do this, let's take it step by step. Let's first ask, what's the derivative of mu n with respect to an? So remember that mu n is just mu of a, which equals mu of wx. So I'll leave this to you to prove. This is not too hard to show that the derivative of the logistic function is just this kind of nice form. It's a times it's sigma A times 1 minus sigma A. This, by the way, is an error in the textbook, should be an N. Okay, so now let's go a step out. Let's take the partial derivative of mu n with respect to WD, that is the dth parameter. So let's write out what mu n is. It's this thing here, sigma of Wx. We're going to use the chain rule here. So the derivative of this whole thing is just the derivative of sigma of an. By the way, don't forget that this thing is just an with respect to an times derivative of an with respect to WD. So this second derivative, that's easy. We just did this here. That's the first derivative of sigma with respect to A. And then the second derivative of an with respect to WD, well, we're taking the derivative of just this linear function, Wx. So this is a sum of a bunch of terms, WD times xnd. There's only one term here that involves WD, which is WD times xnd. So we get xnd here. Okay, so that's our derivative of mu with respect to WD. So we're not quite done yet because what we really want is the derivative with respect, the derivative of log of mu. So we're going to apply the chain rule once more. The derivative of log of x with respect to x is 1 over x. So applying the chain rule here, we get derivative of log of mu is 1 over mu times the derivative of mu, which we did here. So the mu n here cancels with the mu n here. So we get the derivative of log of mu of n is 1 minus mu of n times xn. Notice that we've jumped out from the univariate derivative out to the multivariate derivative. So here we have the multivariate vector here. It's pretty easy. If you just want to convince yourself that this is right, you can do each of the univariate derivatives and show you that it's equal to this thing with xnd at that spot in the vector. We can do the same thing for log 1 minus mu of n. The derivative of log of 1 minus x with respect to x is negative 1 over 1 minus x. So that's what we have here. Then we plug in this thing here. The 1 minus mu cancels, and we get this derivative equals negative mu n of x times x. Okay, almost done. So we are trying to find the derivative of these two terms here. We did that, so let's plug that in. We get this guy and this guy that we showed on the last slide. We can just do a bit of rearranging here. We've multiplied out the terms, did some algebra. We find that this is the sum for each example of mu n minus yn. Another way of looking at is, remember that mu n is our predicted probability for example n. So that's the difference between those two probabilities times the observed features for that example. So this is a very intuitive derivative. We want to push our weights in this direction. The degree to which we got this probability wrong, either positive or negative, if we predicted the probability was high when the true label was 0, or vice versa, if we predicted the probability was low when the true label was 1, times the actual features for this example. So this is essentially, this tells us which weights we can change and in which direction we need to change them in order to push our predictions in the appropriate direction to give us the right probabilities. And by the way, we can write this in a vector notation as well if we want. So this here we have the vector of mu's for all of our examples. So we can do this in vector form too. This is a n-dimensional vector minus another n-dimensional vector times a n by d vector. So this is our gradient of our negative log likelihood. We could try setting it equal to 0. It's not too hard to see that if you tried to do that, you would have trouble finding an analytical solution. In fact, generally, we can't find an analytical solution. So the most common strategy for logistic regression is to use a iterative optimization algorithm, either gradient descent, stochastic gradient descent, or sometimes a second order method that can be a little bit faster. However, note that we're not going to prove this, but this is proved in the textbook, that this is a convex objective function, which is to say that it has a single optimum and that with some reasonable assumptions, we can expect our iterative optimization algorithm to find it in a reasonable amount of time. So even though we're using an iterative optimization algorithm, we're guaranteed a global optimum for the solution. That is, it's worth noting that it isn't always the case that it's strictly convex. We're not going to define what strictly convex is. Sometimes it's required for kind of numerical and optimization reasons to put some L2 regularization. We're going to talk about that a little bit on the objective function. Sometimes it doesn't converge, or it doesn't converge very quickly without that addition. But that said, it is convex objective function, so we are guaranteed a global optimum for this maximum likelihood estimate of our logistic regression.